All right, welcome. This is the 1.3 Practice 1 AP Chem unit assignment that we've got going on here. I'm Mr. Mahoney. So here's the answers that we're going to be going over the 1.3 Practice 1 set. So the first question is determining whether it's ionic and molecular. Molecular is going to be those right side elements that we've got like oxygen, phosphorus, nitrogen, sulfur, all those. The ionic ones are going to be between a metal and a non-metal. And so that's going to be like sodium and chlorine, sodium fluoride, potassium bromide. So you have some sort of metal that's present there. If most of it's on the right side, then no, that's not going to be. Now you could have some that are both, which is a trick question here that they have in some of them. So we'll go ahead and discuss that. But if it's on the right side of the periodic table, it's going to be more molecular, and those are the non-metals. If it's between a metal and a non-metal, that's going to be ionic. So hopefully that helps. So iodine, fluoride. Wow, I cannot speak. So iodine fluoride is going to be present here. And that's a little weird one because the I here, usually if it's lower on the periodic table, it doesn't have that great of wanting a negative charge or electronegativity, and so we wouldn't normally see things. This is an exception because it's usually always wanting electrons. Here it's kind of giving it up. At any rate, I'm not going to go into that right now. Iodine fluoride is the correct name here, and this is going to be molecular because it's both on the right side of the periodic table. CmNO4. So I see a metal here, I see a metal here, but I see a non-metal there. So that'd make me think ionic. The only thing is that this MnO4 group is a polyatomic ion. So I'm in the O4s and all that. So I'm going to go ahead and say both. If you see the polyatomic ions, that's both. That's between the K and MnO4 part. So we've got here. So this is potassium permanganate that we've got. Here we've got cobalt 2, because that 2, remember that charge comes right back up, right to cobalt. And we've got nitrate, and remember this is nitrate. These are all molecularly bound. These are all molecular in the NO3, but in terms of the cobalt and the nitrate, those are actually ionic. So again, this is going to be both. So again, polyatomic ion, PCl5. These are all on the right side of the periodic table. So this is phosphorus, phosphorus pentachloride. I didn't actually put the penta here, so let me actually try that. And this would all be one word, pentachloride. Because we want to make sure that when molecular things that we're actually saying dioxide, like carbon dioxide, phosphorus pentachloride. So that's what you say with molecular things. You have to note how much is there. And this is a molecular because they're all on the right side of the periodic table. This one, because I've got my polyatomic ion as well as I've got my metal, this is going to be both present here. So this is chromium 3. We always look here because this is going to come back up to chromium for the charge. So chromium 3, sulfite. Make sure you know the difference between sulfate, sulfite, and this is going to be both. All right, so we have to know that we have this iron 2 sulfate, but we have to know this heptahydrate. That means it's just surrounded by 7 water molecules, so they couldn't reduce all the water out of it. This one is going to be, we have molecular here, we have ionic here, as well as sulfate has molecular. So this is again going to be both. So typically they might say, is it both is ionic or is molecular? Or they might give you something so easy as PCl5 or NaCl ionic. Or they might say between the sodium sulfate and the sulfate molecules, is it? And then you'd have to say that one's going to be ionic, not between the sulfur and the oxygens. So they might give you a bond. So you can kind of see where you have to think about all of them. You can't just say one or the other. So this is HgCN2 is what I've got here, and this is going to be both. Again, that Cn is going to be that polyatomic ion. Hg is going to be that metal that we've got here. Nitrous oxide, NO, this is going to be molecular, all on the right side of the periodic table, non-metals. We have CuClO2. I'm sorry, it didn't scan in very well. That's ClO2. And I'll go ahead and write it in the CU. CuClO2, this is going to be both because we have the polyatomic ion of the hyperchlorite as well as the we have the metal, the copper. We have ammonia, NH3. This is going to actually just be one. It was incorrect for me to say both. This is actually going to be molecular because it's all non-metals that we've got here. And I know hydrogen sometimes falls on that first on the right side, on the left side of the periodic table, but that's not really a metal. We wouldn't say hydrogen is a metal, or else our air would be metal, which is kind of weird to think about. So this is going to be Na2CO3 times 10 because it's a decahydrate, and this is going to be both, similar to the equation right up here. Let me grab the other pointer so we can actually see. So this next one is going to be dinitrogen. So when it has these things right here, these prefixes, we already know that it's going to be molecular. Those prefixes, the number of prefixes always tell us what it's going to be. So dinitrogen, N2 trioxide, so it's 3 O's. So N2O3 for that one. All right, so then we're going to go ahead and write the empirical formulas that we've got here. And so empirical formulas is going to be the lowest number that all of them can fit into, like the lowest number of all the digits. So if it's like C6H6, it would be CH, which we're going to get to, which is right here actually. So let's actually do this one. Hexacarbon, so 6 carbons, hexahydride, 6 hydrogens. This is going to actually be CH because all of them can be divided by 6 to make that number the lowest, and so it's CH. And that is going to be the empirical formula, but the C6H6 is the molecular formula. So you'll see in here, if it had a different empirical formula than the molecular, I went ahead and changed it. Other than that, they're the exact same. So tetraphosphorus, again, because as that number, it's molecular, tetraphosphorus, so P4O5. And since the 5 and the 4 are not divisible by anything, that's the same as the empirical formula. So the next one, disulfur dichloride, S2Cl2. Those 2's can actually be divided and further broken down to SCl for an empirical formula. The empirical formulas are always scaled by some whole number ratio, and in this case it'd be 2 to get up to the molecular formula. Tetraphosphorus trisulfide, so tetra, so P4S3, these cannot be divided by anything, so that is the same as the empirical formula. We already did D, so let's go to tetraarsenic hexaoxide, and so we're going to have these that can be broken down. The 4 and the 6 can be divided by at least 2, and we get As2O3, so that's going to be a multiple of 2 to get there. This last one was describing what's the three-dimensional trigonometry, and we can actually see that this TD is tetrahedral, that I've got for both of them. This is the bond line formula, the wedge and dash shapes, showing that this dash is going back behind in the plane, and so that would be something like this guy going back behind, or this one going back behind. This wedge is this one coming out at you, and this one would probably be sticking straight up. So this would be sticking straight up, and this is the wedge coming right at you, right there. But they're all tetrahedral. So this has been the 1.3 practice set that we have for AP Chem, the practice 1 set. So if you have any further questions, please let me know. Other than that, have a fantastic day.